macromechanical analysis of lamina. Okay. So from last two lectures we are discussing about what is meant by macromechanical and what is meant by micromechanical. That particular thing already we discussed. As far as concerned with this macromechanical, then analysis and lamina. So now we all are familiar with these three words. What is meant by lamina and what is meant by laminate? That difference already we have understood. Number of such laminates. Normally we may consider that these are very small in thickness, 0.14 mm. Is it okay? What lamina dimension we are considering thickness? 0.14 mm. Like this, very thin, means for 1 centimeter there are 10 mm, and out of which 1 mm if we take into consideration, then we are going to divide that into 10 parts, and out of which one part, near about 1 to 2 parts. So that much small thickness of this lamina is having, and laminate is having, and number of such laminates will be compiled together in order to form one lamina. Is it okay? So one lamina may have number of different layers, maybe 10 number of layers, 15 number of layers, 16 number of layers, 20 number of, like this number of layers of such laminates, one another the another will be kept like heap, and then whatever the construction will get formed, so that is the lamina. So for that, what is essential, that whatever the layers of the laminates, that should have strong binding with each other, and that binding of different laminates with each other will give the strength to that material. So lamina, that concept we have understood now. Now the analysis which we are now interested, inside which we are not interested in micromechanical, but we are interested in macromechanical. So whenever it is at constituent level, that means if we take the concept properties of the matrix material, if we take the concept of reinforcement material, then combining the properties of matrix and reinforcement together, whatever the properties we will get, so that we are calling as micromechanical analysis, means the kind of analysis in which we are taking the part of constituents like matrix reinforcement into consideration, and then we are identifying the properties of this composite material, and then we are identifying the behavior of the composite, then that will be considered to be the micromechanical analysis. But in present case, we are studying as a macromechanical. Is it okay? We are considering that total body as one constituent. Here we are not giving the scope for matrix and reinforcement separately. Means behavior of reinforcement or behavior of matrix, we are not identifying separately, but as a constituent of that, whatever the one element we are getting, we are considering this as one composite, and behavior of that total composite lamina, that together is analyzed, and for that it is considered to be one specific body, and by that way what analysis we are carrying, that is the macromechanical analysis. So while carrying that macromechanical analysis, with the concept which we have already studied, inside that in solid mechanics or in analysis of mechanical element or in strength of materials, few concepts we have already studied. We have certain assumptions in that. Whenever we studied the analysis of mechanical element or the part of solid mechanics, this assumptions where material is isotropic, homogeneous, there is no any flaw, there is no any kind of porosities, it obeys Hooke's law, material is continuous. So like these dimensions are same in all directions. Like this, we already have certain assumptions. In this case, where as far as concerned with the composite material, it is not the case that this particular composite material may be isotropic, because as reinforcement phase is going to remain as inherent phase, and it is not going to be have a miscible properties inside the matrix material, because in alloys what we say, whenever two alloys are combined with each other, suppose one is the parent material and another is some additional material which will give the homogeneous structure. But as a reinforcement is not going to form any kind of homogeneity with the matrix material, that will remains as an inherent phase, different phase, and that's why here we will not consider this as an isotropic material. So that is the one limitation in front of us. Is it okay? As a composite material. So for that purpose, whenever we consider the isotropic and anisotropic material, these are two different materials, then exactly what is going to happen in order to separate out the material as a isotropic, material as a transversely isotropic, material as a monoclinic, material as a orthotropic, and material as a anisotropic. So like these different nominations we are going to give for this material, and mathematically how these are relate with each other as per as concerned with the different properties, stress strains, and by that way how this follows the Hooke's law. That part is very interesting in macromechanical analysis of a lamina, because up till now during last lecture also we studied that whenever we are considering the uniaxial, biaxial and triaxial. So last time we discussed about the triaxial stress system. So whenever the system is triaxial stress system, like this, whenever we are considering the, suppose this is any part, cubic part, and inside which the sigma 1 is the stress along x-axis, sigma 2 is the stress along y-axis, and sigma 3 is the stress along z-axis. So these are three stresses. As these three stresses are present, definitely on all these three direction forces are has been applied, because in each case always we consider that stress is equal to force upon area. As stress is present, definitely force is present. Sigma 1, sigma 2 and sigma 3, these are three stresses. That means P1, P2 and P3, these three forces are already applied on this particular body in three different directions. Suppose in X, Y and Z direction, all three directions, three different forces are acting, and that three forces are creating the stresses sigma 1, sigma 2, sigma 3. Then that forces will create the strains, because due to this force change in length is going to happen, and this change in length to the original length, that particular dimension we are considering to be the strain. So strains are present in all three directions. Whenever we are going to calculate the strains in all three directions, then here not only, because if we take the consider unilateral uniaxial system, only uniaxial system if it is there, then there will be no any relevance of transverse directional forces on longitudinal direction. But for biaxial, that is going to definitely going to take into consideration, triaxial also we will have to take into consideration definitely. So effect of forces acting on P2 and P3 in the direction of P1 or X1, that is going to make the effect definitely in terms of the elongation or deformation of the body. And that particular deformation in the direction X, what is going to happen as the effect of these two forces P2 and P3, so that if we consider that P2 and P3 are the longitudinal, if these are the we are considering that tangential type of forces, is it okay? So sorry, tensile type of forces, not compressive. Sigma 2, because here in figure also sigma 2 and sigma 3 are tensile, not compressive. That's why effect of these two tensile forces in the direction of X will be to shorten the length. Is it okay? So, but the effect of P1 is to increase the length. So length will get increased due to the effect of P1, but it will decrease due to the effect of P2 and P3. And that's why effective strain, which is going to be calculated, So for calculating that particular strain, epsilon 1 or epsilon 2 like this, what we consider that that particular strain as presented on the screen here, you can see that E1 is now given as sigma 1 upon E minus mu into sigma 2 upon E minus mu into sigma 3 upon E. Is it okay? So if we write here separately this, then we will come to know here. Suppose this one is the sigma 1, sigma 2, sigma 3 like this. Let us have, let us check here. So here, if we consider this much portion only, sigma 1, sigma 2 and sigma 3. So I am taking this particular snapshot only, epsilon 1 to this one. So let us discuss on that, so that see the equation sets now I have taken separately here. With these equation sets, the strain along x direction, E1 is the strain along x direction, E2 is the strain along y direction, and E3 is the strain along z direction. Then E1 is sigma 1 upon capital E minus mu into sigma 2 upon capital E minus mu into sigma 3 upon capital E. As far as concerned with E2 and E3 also, by same way, for E2 sigma 2 will be in tensile and remaining 2 will have the transverse effects, and that are related with the Poisson's ratio. So during last lecture we discussed about that lot, and that's why now if I want to form the relationship here, then what happens exactly, that we will try to understand here. Is it okay? So let us have the small matrix here. Is it okay? If we consider that there is small matrix where E1, E2 and E3 we are taking into consideration, then let us see here what is going to happen here. So I will come to the exact matrix value here. See here, epsilon x, epsilon y and epsilon z. Here E1, E2, E3 are nothing but epsilon x, epsilon y and epsilon z only. Now how this epsilon x or E1, here it is represented as E1, but it is epsilon x. How it is represented or how it can be related with sigma 1, sigma 2 and sigma 3? If suppose we consider, for the sake of simplicity, if material is isotropic in nature and if forces are same, then stresses will also same. Is it okay? So suppose dimensions of the cube are same, forces are also same, then as dimensions are same, area will also same. Is it okay? Are you getting the things what I am saying? मला काय म्हणायचं लक्षात येते तुमच्या की जर डायमेन्शन सेम असतील, if all dimensions are same, then definitely area will also same, cross sectional area will be same. Suppose we take into consideration one cube, and for that cube if it is its length, width and thickness, all these three dimensions are suppose 3 centimeter. Then whatever the cross sectional area, if we take any way cross sectional transverse direction, then that is going to happen 3 into 3. That means area will be same. Force applied P1, P2 and P3, that forces, suppose these are same, these are equal to P, then force upon area, that stress will also same. In that case, sigma 1 is equal to sigma 2 is equal to sigma 3 as per as concerned with this particular E1. Suppose we are considering this only portion, then what is going to happen? The E1 will be represented, E1 will be considered to be a in terms of this 1 upon E, sigma and sigma 3 and sigma 2, all three sigma are same. We take sigma common, in bracket it will be 1 upon E minus mu into 1 upon E minus mu into 1 upon E. Is it okay? Now let us come here, 1 upon E minus mu upon E minus mu upon E. Here besides mu, This gamma is used as a Poisson's ratio. This is the notation used here as a Poisson's ratio. Is it okay? So, are you getting this? If I am writing in the form of matrix, then what is going to happen? Because what? In solid mechanics, already we studied the different strains. So what sigma x represents? Sigma x represents the strain along x-axis. Sigma y, what sigma y represents? Sigma y represents the strain along y-axis. Sigma z represents the strain along z-axis. Gamma xy. So this gamma here will be yz, zx and xy. So this gamma yz, what this represents? This is also one kind of strain, which is shear strain. Is it okay? And zx, that is also shear strain. So three shear strains here in this matrix, epsilon x, epsilon y and epsilon z. These are three strain that are the strain along x-axis, strain along y-axis and strain along z-axis. So with these three strains which are in x, y and z direction, and these are three strains which are shear strains. So three shear strains and three regular strains x, y and z direction. If we take into consideration, if we take here, then we will come to know that I am going to identify all these strains and at a time. Then I am formulating one matrix structure, and with that matrix structure, I will come to know any strain here. Means suppose I am solving now this matrix. If I want epsilon x, then I will take first row and first column. Is it okay? Are you observing this particular matrix? हा matrix सगळ्यांना लक्ष देतोय? हा matrix लक्ष देतोय का सगळ्यांच्या? See, epsilon x, प्रत्येक element आपण now we are going to identify each and every element. If we are identifying epsilon x only, suppose this particular epsilon x I want to identify, then what I will do, I will multiply this first row with first column. For epsilon y, second row with this column. Epsilon z, this third row with this column. Likewise, for these three strains, fourth, fifth and sixth row with this column, we are going to multiply here. Now with this multiplication, what is going to happen here if we try to check? So epsilon x, for that 1 upon e into sigma, means sigma x upon capital E minus mu into sigma y upon capital E minus this mu into sigma z upon capital E. Is it okay? So see here, this is mu. Is it okay? So mu is like Poisson's ratio. Here also this is also notation mu. Here only capital and small mu. As far as concerned with this, here it is considered to be mu, but this is capital mu and this is small mu. So epsilon x is equal to sigma x upon capital E minus mu into sigma y upon capital E minus mu into sigma z upon capital E. Remaining three terms, there is no role because this tau which is shown here, that is the shear stress. As far as concerned with this stress, sigma x is the stress along x-axis, sigma y is the stress along y-axis, sigma z is stress along z-axis. These are these all three stresses are we will consider as shear stresses. Is it okay? So yz, zx and xy, all three are shear stresses. So gamma yz is related with this tau yz. Now for that purpose, we will have to multiply this particular row with this column. 0 into sigma x 0, 0 into sigma y 0, 0 into sigma z 0, tau yz upon g. So gamma yz is equal to tau yz upon g, and for remaining two, if we take the multiplication, that is going to become 0 into tau zx and tau xy into 0 like this. Gamma yz is equal to tau yz upon z. This simple relation, because we all of know that What is shear modulus? Shear modulus is shear stress upon shear strain. If we try to validate with this particular matrix, then definitely we will come to know that the shear stress tau yz upon shear strain, that is the gamma yz. Here, if I am multiplying with this particular gamma yz with this fourth row, then I am getting here gamma yz upon z is equal to tau yz. Or if I am trying to take the shear stress upon shear strain, this particular value, then that's its answer is equal to shear modulus, which is same for this gamma zx and tau zx, gamma xy and tau xy. So all these three shear stress are related with each other by shear modulus. So with this shear modulus, shear stress upon shear strain, that particular equation we will get with that multiplication. So that's why if we try to verify each and every column multiplication, each and every row multiplication with the column, then the concerned value we are getting. So epsilon x, as we are considering sigma x upon capital E minus mu into sigma y upon capital E. So same thing we will get here. So sigma x upon capital E minus mu into like this, same thing we will have here, that is sigma x, sigma y, sigma z. Is it okay? Here sigma x, sigma y. So if we consider sigma 1 as sigma x, sigma y, sigma z, then this 1 upon E is going to remain as material property, minus mu into E is going to remain as material property. So what we understood with this matrix is that the first matrix which is shown here, if we consider this particular matrix, I am marking here this particular matrix, you should just check here this particular matrix, whatever the shaded now this portion, what is the colored portion is now here, this particular matrix which shows only material properties. This particular row only shows strain values. This particular row only shows stress values. So the strain and stress, and in between that this particular big matrix which is going to represent as the material properties. So 1 upon E minus gamma upon E, because E is Young's modulus and Young's modulus is nothing but the material property that all of we know. Then this minus mu, that is also material property, and so that's why minus mu into V, that is also material property. So here 1 upon G, that is going to also add due to the material property. So this particular matrix will get calculated based on the material properties, and the relationship between stress and strain will be ensured with this matrix of material properties. Is it okay? So here now we have generalized, we have formulated the relationship between stress and strain, and that we have expressed in terms of matrix. So what advantage we will get by using the matrix here? Simultaneously we will get all the stress, all the strain values based on the stress. Is it okay? If we use this particular equation here, then that equation definitely give us the directly property, the strain values, if we know the material properties. Means suppose I am using steel here, definitely if stresses are available, the for steel I know what is E, what is mu, what is Z. So all these properties I know for the steel, for brass, for bronze, for copper, for anything, that I know. But if I want these particular properties for composite material, then for that some different thing we will have to think about. Because whenever we are formulated this relationship in matrix form for stress and strain relationship, we have assumed that these are the isotropic material. Is it okay? These materials are the materials are isotropic in nature. Is it okay? A relationship between stress and strain through these material properties, which represents the isotropic. Is it okay? Same thing is repeated here. See, we are going to what is happened in as far as concerned with this 2.17 and 2.18. What is different? Different is that this is strain to stress relation. Here it is stress to strain relation. Means in 12th science, whenever we were studying about the matrix, we are familiar with identifying the inverse of the matrix. What is inverse of the matrix? That stages we followed in order to identify the inverse of that matrix. So same thing are carried with this 2.17 and this particular strain are multiplied by with one unit matrix. The operations are performed on this matrix in order to form the relationship between stress and strain, because it is relation between strain and stress. By multiplying, by converting this particular matrix in unit matrix and by multiplying by unit matrix to the strain matrix and performing the steps, whatever the matrix we are getting, that matrix is like this. Is it okay? So here we can understand how this particular stress is identified based on the strain. If strain is known, how to identify the stress? So for that purpose, E into bracket 1 minus mu upon 1 minus 2E 1 plus 1 minus 2 mu 1 plus mu. Is it okay? So here we can understand here that Young's modulus, Poisson's ratio, how these are related with each other as far as concerned with the stress sigma x. Is it okay? So in order to identify the sigma s, this first row and first column. So this particular first row element with this element, if we multiply this particular element with this one, this element with this one, this element with this one, and remaining three elements with this 3 1, then we will get the particular value of sigma x. So first row and first column, second row and this column, third row and this particular column. With this, we are getting the value of sigma x, sigma y, sigma z, tau yz, tau x, tau zx, and tau xy. So respective values of that particular stresses, with the help of the strains, we can identify by taking into consideration this particular matrix. So these are the one. This is only the difference between the equation number 2.17 and 2.16, where this mu is Poisson's ratio is Young's modulus, and with usual notation stress strain and G is shear modulus. Is it okay? Now our interest is different. Is it okay? Whatever the equation we have formed here, whatever the equation we have generated here, with that equation or with that form, if we are identifying the properties of the material, then our assumption is this material is isotropic material. Now we are going to generate one more equation that will be applicable for different kind of material categories. For that purpose, there is no such a relationship between the stresses and strain in which each and every element, now for example, now whatever I want to tell here, in that just understand first row, suppose epsilon x, then for identifying epsilon x, 1 upon e into sigma x minus v into minus mu into e upon sigma y minus mu into e upon sigma z. Here it is 0. This portion is 0 here. So that recommends that there is no relationship between this portion with these shear strains. But it doesn't happen whenever the material is not isotropic. Is it okay? There will be certain elements present, and that is going to make an impact in order to identify the stress strain relationships. Is it okay? Whenever material is isotropic, definitely the strain energy possessed by that body, so that is given as, this is the strain energy. We all of we know that how we have calculated the strain energy inside that, the multiplication of stress and strain that we carry. So sigma x, sigma y, sigma z, like this multiplication of stress and strain, that is given here. Now just see here that, in general, whenever we are calculating the energy, in strain energy, sigma square V upon 2E, like this equation we have used. But definitely that is multiplication of stress and strain, because we take under area under the curve, and that area under the curve is the multiplication of sigma x, sigma y, and normally we take the average of that. Initially it is 0 and finally sigma x into epsilon x, average we are taking, and that's why 1/2 we are taking into consideration. So this is the strain energy which we consider here. So before going to other kind of material property, or before going further, for other kind of materials, that is which we are repeatedly using the words isotropic, transversely isotropic, then monoclinic, then orthotropic, and then anisotropic. So for each and every type of categories, now how these relationships are building, how these stress strain relationships are forming if the material is monoclinic, transverse, isotropic. So that part is very interesting part, and that we are going to understand with coming lectures. But before going further, let us have one example which is in front of you. Just read that example. What is given here? That consider a bar of cross section A, length L. See here, this is the bar of cross section with cross section A, length L. Now load P is applied on two ends of the rod. Find the state of stress and strain energy per unit volume. Is it okay? So here, in general, how to calculate sigma x, that we know sigma y and sigma z is absent here. No any kind of shear strains are present here. As far as concerned with this particular equation, which we have already used in order to describe the relationship between stress and strain in terms of matrix form. So for that, the strains is a vertical column here, the stress, which is P upon A, because P is the load applied, A is the cross sectional area. So that's why sigma x is like that. For y and z direction, no there is any forces applied, and shear strains are also zero. That's why this remaining total column here, which is shown here, that will be zero here. Is it okay? So like this portion will be zero. In order to calculate the sigma x, first row, first column, sigma y, second row, this column, third row, this column, like this. After getting that multiplications, what we get, that is the sigma x, like this, sigma y, epsilon x, epsilon y, epsilon z. These are the strains. Now if we multiply this, and if we get the value of strain energy, here we are getting 1 of sigma square V upon 2E, like this equation of the strain energy we have already formed, because in analysis of mechanical element we have studied the strain energy and impact loading, and whenever we studied that particular equation of strain energy and impact loading, at that time whatever we discussed, whatever assumptions we made, whatever the equations we formed, that equation was sigma square V upon 2E. That is the equation of strain energy, where V is considered to be volume. Here in this case, we are considering strain energy stored per unit volume. Is it okay? So here this particular word is very important. Strain energy stored per unit volume of the rod, and that's why in order to calculate that particular strain energy stored in the rod per unit volume, so for that purpose, what is going to happen here, that with this multiplication, this V which is not present here, that means if per unit volume we are considering, so with that volume, this particular equation has been divided by, and with that division, we will get 1 half sigma square upon capital E. Is it okay? So, with this 1 half sigma square upon E, this will be represented as strain energy per unit volume. Is it okay? So total strain energy in that case, for the in order to calculate the total strain energy, we will have to multiply by volume to this equation, so that it will be 1 half sigma square V upon E, or sigma square V upon 2E, so which is validated with this particular example. So this example is purposefully taken here in order to validate, because this matrix which we are writing here, we are validating this matrix, whether this matrix is correct or not, or any mistakes are there, whether these particular equations of strain energy which we are identified already with the assumptions of analysis of mechanical element, whether all these assumptions are applicable, and whatever the answer we are getting as a strain energy, whether same answer we are getting or not. In order to validate that, this particular equation we have taken into consideration, in which this particular, in general, length is L, load applied is P, cross sectional area is A, and then for identifying the stress along X, Y, Z axis, as well as shear strengths in three directions. So for that purpose, we have multiplied this particular equation, first row, first column, like this, and we got the strength along X direction, Y direction, and Z direction. Likewise, shear strengths, and then the stress and strains are multiplied here, and with that multiplication we got this particular equation here. Is it okay? Now for next lecture we are going to observe the nature of Hooke's law, how it is different for different kind of material. So from start of this lecture or from previous lecture, we are always taking the different types of materials, the names of different types of materials. We are continuously repeating: isotropic, transversely isotropic, monoclinic, orthotropic, anisotropic. So these are different type of materials which we are considering. Then in general, whenever we are writing the stress strain relationships, then in that stress strain relationship, if stress is given along x, y, z axis and three shear stresses taken into consideration, then sigma 1, sigma 2, sigma 3, tau 2 3, tau 3 1, tau 1 2, which is related with epsilon 1, epsilon 2, epsilon 3, gamma 2 3, gamma 3 1, and gamma 1 2, with this C matrix, and this particular matrix is considered to be a stiffness matrix. Is it okay? So always take into consideration that particular C matrix which is shown here, that is considered to be stiffness matrix, and these are 6 by 6. Is it okay? In that particular matrix, so 6 by 6, where 6 by 6 matrix is called as stiffness matrix. So how many constants are there in this matrix? In this matrix, total 36 constants are present. Is it okay? So C11 will be regarded as one constant, like this C12, C13, all these are regarded as a constant. So each stress value is having relation with each strain value with that stiffness metric, which that stiffness element. Is it okay? So 36 such elements are present here, and these are related with each other, and which element will be strong and which element will not take into consideration in which kind of material, that is the part of interest, and that we are going to understand with coming lecture. So let us observe this particular equation and for next lecture we will continue with this. So anybody any doubts in this? Anybody any doubts?